So your probability formula sheet, definitely want to have this guy. I want to remind you, though, when I give you a problem like that chart problem, dear God, I think we looked at, I might have forgotten to do this last time. When I ask you an AND question, if you have the chart to look at, you do not use this formula. That's insane. Right? You just look, how many do both? That number, the intersection, that's the answer. I just look for that, right? If you use the formula correctly, it will come out okay. Why do that to yourself? So A given B. Same thing with A given B. If I have a chart to look at, and I say given men, that just means your whole world is the dudes, right? So you just kind of cover up anybody else. Hopefully just one more category, right? Let's see, what am I missing? Am I missing anything?
No.
Anybody have any more to put up there?
I have a question.
Yes?
Yeah. Isn't it easier for you to just put it on the board and just see that?
No.
No, not really. Because what you're going to do is you're going to make sure that it's good, and then on the final, you're just going to bring all your formula sheets with you, and you got them all for the final.
Yeah.
That's not a formula. That's an idea.
Did you read it?
What's that?
I'm just kidding.
Anything else? That's all I can remember. If nobody says anything, that's it. That's all I can have. Right? If you have anything else on there, it's no good. Okay. Okay. So we got that? Almost okay. All right, we good? I want to do one more example from section 5.2. That's the x, p of x stuff. And I also want to tell you one little thing, one little terminology thing. Who remembers the formula for the mean when I have x and p of x and all that kind of stuff? So who can look it up real fast?
The sum of p of x.
Minus.
Yeah. So it's the sum of x, p of x.
Yeah, that's it.
So what I really like is the fact that we're going to start using a different name for the mean sometimes. We're going to call it the expected value.
Why?
There's so many
Yeah, that is a
different
very
words.
excellent question.
So if you ask yourself, what do you expect? In fact, I've used that same language before. What would you expect to have happen? If you had 400 kids, 400 babies born recently, how many would you expect to be girls? That's your expected value. That's also the average number of girls out of 400. So it's not just a new word. It's not like I'm bringing a new word. It's not like I'm using a new symbol. It's just another way to refer to the mean. Is that a better way to say it? Mm-hmm. So it's just the way I said it. Secondly, you just accept that. Right? So it's expected value. And what's really nice is the first three letters kind of get you there. Right? So if I ask you for the expected value, you've got the formula sheet, EXP. It tells you use me if he asks you for the expected value. That's the mean, right?
Oh, that's cool.
That tells you that expected value is the mean. Because again, we've done this before. If you flip a coin 1,000 times, how many would you expect to come up heads? 500. Because if you had a lot of people do 1,000 coin tosses, you would get on average 500 heads. So that average is another way of referring to the expected value of something. Okay. So very often they use these these probability distributions. For example, what happens when you're 25? Something magical happens.
You can rent a car.
You can drive a car. You said rent, but you can suddenly drive a car better. How do you? What am I saying? What happens when you're 25? Do you guys know? Anybody not 25 yet? A lot of you guys. Your insurance goes down. All of a sudden, you wake up on your 25th birthday, and suddenly they say, "Oh yeah, you realize how to drive now. Good job," because your premiums go down. Right? I still remember that. It was like, I can eat something beyond ramen noodles. Yay! So, grad school was, just whatever money you got left over is what you got. So they use probability tables. So they say somebody aged this to this has a much higher chance to be in an accident than somebody aged this to this. And they kind of see how much money would we have to pay out on average in those kind of accidents. And they kind of use that table to figure out what the premium is going to be set for these different age groups or these different groups based on where you live. So when you get your insurance, you have to tell them how old you are, what do you drive for, what purpose, because that actually affects how you drive. Where do you live? Because, of course, you live in certain areas and it could be worse for you in your car, as we discussed earlier. So another place this is used, could be used, would be for gambling games, lotteries. So if I had a lottery where there were 1,000 tickets sold, and there's only, let's say, they have three situations here. Let's say there's 3 tickets win $500, and 1 ticket wins $10,000. And we want to figure out what price to set the tickets at so that this is a wash. And so if we want to make money, then we just set the price a little higher than that, right? So we want to find like the bare minimum ticket price so that we could afford that. How are we doing so far? So this assumes we're going to sell all 1,000 tickets, right? Does everybody understand the basic setup?
Yes.
Are you in this room with me right now?
Yes.
Yes. Okay, good. Yes. So what is the probability that I win the big jackpot? Oh.
How? Never mind. I was like, how did 1,000 tickets get sold?
So it's probably I win $10,000. What's that probability?
1 in 1.
What of that? There's only 1 ticket out of 1,000 that's going to do that for you. What's probably a win? $500.
3 in 1,000.
3 out of 1,000. So what's probably that I lose?
It is 996.
Good, 996, because there's 4 tickets that actually win something. So there's 996 losers, right? Okay, so you will have some problems where they're not going to tell you the probabilities, but they're going to give you all the numbers you need to set up your own probabilities. You just have to be sure to get all the situations. So in any kind of lottery situation, it's going to be a lose, but then there might be several winning categories. Maybe you win a car, or you win a goat, or you win whatever. Somewhere that might be a good thing. So now if I can make it look like this, then I know what kind of math to attack it with, right? So my situations are lose, win big, or win some. That's my quick way to say that, right? Those are the 3 situations, right? So if I lose, how much money do I make?
0.
0. Good. If I win big, I'm going to win $10,000. And if I win some, it'll be the $500. And then, of course, next to this, what's the probability that I get $0? 996 out of 1,000. So probably I get $10,000, 1 of 1,000, and 500 is 3 of 1,000. Now this is a very small list, so you shouldn't have to use your L1, L2, L3. We should just be able to do this directly. So this column is going to be what? X times P of X, because then I just add them up to get my expected value. So that would be an expected value for a lottery ticket. Okay, cool. This is kind of important because I tried to give the example before about if you play poker, if you really want to make money, you've got to play poker for a long time. Because you always attack it with kind of the best situation. You can kind of play off of being able to read other people. Let's just pretend you're like me and I can't read anybody, right? I'm a horrible poker face, so I shouldn't play poker in the first place. If I just always play the odds, if I play in a way that I win 60% of the time, that means I'm going to lose 40% of the time. And if you imagine how many hands you've got to play, if you don't know anything about poker, you play a hand, and you play another hand, you play another hand, people lose and they leave if they lose all their money. So all the hands I've got to play, over time, I'm going to leave a lot of this stuff. I've got to play the odds. 60% of the time I'm going to win, but I'm going to be playing like a lot of hands. So I'm going to lose at some point a lot. And that's why you have these people. If you ever watch poker, you have these people, you don't even know who the hell they are. Came out of nowhere and won everything. And then they're gone. They disappear. And that's because of that. They just lose somewhere early. They're playing the odds, and the odds are going to be against them sometimes. So here, if I multiply across, I get 0. What's here? 10?
What? No.
So that's 1/2 of 3. So it's $1.50. So what this means is if you add these up, I get the expected value of a lottery ticket. Now I really want you to understand. If I say I get 50% heads, 50% tails, that doesn't mean a damn thing for a single flip of the coin, right? Probabilities only make sense if I do something a lot. And that's sort of related to what I was talking about with the poker playing. So if I flip it 1,000 times, now I can start to see the 50-50 kind of coming out. Or I should be able to if it's a fair coin. Here, this is my expected value for any lottery ticket. So if I play this game, so this is actually if it's free. Because how much do I lose if I lost? 0. So this is assuming a ticket doesn't cost anything. What are the people going to at least charge for this ticket?
$11.50.
Yeah, if they charge exactly $11.50, then my expected value is 0. Now, actually, what are they going to do even better than that?
Charge you $15.
Yeah, charge $15, so they end up actually making some money, right? You guys kind of see this idea. But this is the way, if they do make it, let's see, if they were stupid, or if they didn't know how to do this, and they charged $10 per ticket, my expected value for a ticket would become $1.50. And what that means is, if I played this thing 100 times, I would make, on average, $150. Every time I play, my average earnings should be $1.50. So if I play this thing 100 times, I should get, on average, I should get $150 at the end. You guys kind of with me? And that's because, on average, if somebody's going to win the lottery, it's not normally somebody who just comes out of nowhere and played it for the first time. It's somebody who's been playing for a long time. Or you walk into a casino and you see those desperate, depressed people, and they can't even pull this in. It's just do a button they press. And they've been there all day, and they win $4 billion, but it doesn't matter because they already lost $7 billion, so who cares? Right? So that's the idea. Over time, I'm going to lose some, but if I hit once or something, one of these guys, that kind of makes up for it. So overall, I'm going to come out ahead if they don't charge enough. So if you do any expected value for any casino game, what do you think the expected value for you is going to be? You go in and you play a game, your expected value, they're all going to have the same kind of relationship. They're all going to be negative. Right? Because where's that money flowing? That negative, from my perspective, means it's money flowing away from me. And of course, that money is going to the casino. And they're all very happy. Here's a drink for you. We can afford it because we just taken all your money. It's okay. Right? Just loosen up your judgment a little bit so you spend even more money. Okay. So you do have, I think, at least one, if not two, Homer problems very much like that. Like a lottery kind of problem. So you have to set up your own probabilities. Okay? Fun? Okay, good. And I want to talk just a little tiny bit about section 5.3, and then we're going to head out a little bit early. And we're getting ever so close to the most important chapter in this book, which is chapter 6. Chapter 6 is where we really learn the meat of what's going to help us do a lot of this testing. In fact, very soon we're going to learn how to calculate probabilities that the book keeps doing. Like it says, probably going to get 200 heads out of 500 tosses of the coin is 0.02 whatever. And somebody was asking me, how did they do that probability? We don't know yet. We're going to actually be able to do it when we finish chapter 5. So today we're going to talk about binomial probability. And what do you, binomial.
2.
I love it. So these are probabilities that have exactly 2 outcomes. Now you can make almost anything become binomial. So obviously flipping a coin is binomial, so only heads or tails. Rolling a die could be binomial if I say 5 or not 5, right? Say again? Evens odds. So there's a lot. As long as you can break it up so it covers everything and in opposite situations, you're golden. That's the idea with binomial probabilities. So let me kind of step us into this using something we already know. Probability that somebody's left-handed. Last time I looked, it was 11%. It's like 10 or 11%. How many people in here are left-handed? Did I give up again? Oh, wow, look at that. 1, 2, 3, 4. Okay, I'm not. There's roughly 48 people here, sure. 4 out of 48 is 1 out of 12. What's 1 divided by 12? Yeah, 8.3%, roughly, right? 1 divided by 12, yeah. So it's not too far off from that, right? And I wouldn't expect it to be head-on this. I wouldn't be freaked out if there were no left-handed people in here. Would we? Would anybody be freaked out if there was no left-handed people? Now, if I had a stadium of 800,000 people and there were no left-handers there, that would freak me out a bit, right? How many would I expect if I had a stadium of 800,000 people? Yeah, that's really going out on a limb. Exactly how many would you expect?
88,000.
Yeah, how'd you get that? Yeah, just take 11% of 800,000. I expect that. Which means what you just did, and I'm getting a little ahead of myself, but this is okay. What you just did should be the what? That's expected value, which should be the mean. So what did we just do? This is what? What symbol would this have in statistics? No? That is the what of people? The number of people. So that would have the letter
P.
That's the size of my group of people.
Population.
That would have the letter N, right? N is the number of people I'm talking about. So this would be N. And this, actually, incredibly enough, would be P. So it looks like later we're going to learn that N times P is the mean. So if I make 60% of my free throws, I used to beat up on Shaquille O'Neal because he was a Laker. I hate the Lakers. It's too bad if you like. And I'd say if he made 30% of his free throws, right? It means he improved. 30%, and he took 20 free throws. How many would you expect him to make? 6. 30% of 20, right, is 6. So that's how many you would expect him. That's the average number he would make. So if he made 19, that would be freaky, right? So we know exactly what unusual is. How many steps do I have to go out? 2 steps. So if we can figure out what the standard deviation is, I can figure out exactly what's unusual. So remember, there was a problem in the homework, and we've talked about this kind of thing before. If I expect 200 heads when I flip a coin 400 times, how far do I go away from that before it starts to be unusual? Is 205 heads unusual? Is 211 heads unusual? 390 heads is definitely unusual, right? But somewhere in there is the line, and we'll be able to calculate what that line is. All right, well, let's take a step back. Let me go ahead and use that symbol. Let's call this P. And that symbol P represents the probability of success. A success doesn't have to be a happy thing. It could be a dead person. It could be somebody with a sickness or no. It's just the thing that I'm looking for. If I find it, it's a success. So in this case, I'm looking for left-handed people. So the probability of finding that is 11%. So what's the probability of not finding that, which we'll call Q? 89. So this is the probability of success, and this is the probability of failure. Okay.
Wait, did you say Q or Q?
This is not a Greek letter. It's the letter Q.
Okay,
Right.
because I was like, man, it's like mu now.
I like it. That would be so awesome. A cow that smelled something funny. So if I have, let's say I pick 5 people at random. And I want to know the probability that at least one, no, Jeff, no, exactly one is left-handed. So somebody came into my office earlier, and they were asking me a question about, in the book it said probably exactly this many heads is .02 something. And a really good question she had was, how did they figure that out? And I said, we don't know yet. They just gave it to us, but now we can do it. Now we're going to figure out exactly how to figure out probably exactly one left-hander. Or probably exactly 5 6s if I roll a die so many times, so forth. So we're going to start off with a very basic way of doing this, which is we're going to try to quickly come up with a better way to do this. How did we do this just a minute ago? If I want exactly one left-hander and I got 5 people, how many ways is there for that to happen? If I pick 5 people, I can pick the left-hander first, or I can pick the left-hander second. So if I pick the left-hander first, what do all the other people have to be to match what I'm looking for?
Right.
So that'd be Q, Q, Q. So one way I could do it is the first one is a left-hander, and the second one is not, and the third one's not. So that's why I'm multiplying here. Is that cool? Because that's one situation. So the first one's left, and the second one's not, and so forth. Or what's another way for this to happen?
Q, P, Q, Q, Q.
Q, P, Q, 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 or Q, Q, P, Q, Q. Aren't you happy we don't have 11 people? Or Q, 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 P. Is that everybody? Just float that P through. Are you with me? That sounds very strange. But sounds more like maybe a nursing class, I don't know. Or something even worse. Now, mathematically, what do they all have in common? I actually wrote the same damn thing 5 times from math's perspective.
It's one of
Use a little bit of algebra. How do you rewrite every single one of these? P times Q to the 4th. So all of these. So it's PQ to the 4th. And how many of them are there? 5. So the total probability for this would be 5, because there's 5 ways to do it, times P times Q to the 4th. Now look at I really want you guys to realize what this says. This number is how